Microphone is working? Yeah. I have a very fun one for us today. This is chapter 17. There are 18 chapters in the book. This is the second to last chapter. This is probably the most complicated chapter of the book. It is going to take a lot of thought to explain it well, and it took a lot of preparation to get the slides and the code in this way. It is about a topic called classification, which is very, very similar to regression. We've been doing it's the idea of predicting something. We've been dealing with that a lot already. But we've been predicting numerical things so far. All right, we've been predicting numerical things so far. What if we wanted to predict categorical things? That's the question. That's the question of this chapter. And this leads to like the ideas of basic machine learning. And that is a nice highlight to the semester, I think. So a lot of important information in this chapter. Please start reading chapter 17. And with that in mind, I'd like to release Project 3. Project 3 is the last and final project in the class. There's only 3 projects. You're still working on 2 if it's not already due. I don't remember. I'm going to release Project 3, and I'm going to have it be due the last day of classes. All right, so the Friday before finals week begins, I'll have it be due that time, which I think is going to be, we are in week 13, no, 14, right? 14, 15, 16, 17, so the 5th. I'm going to make it be due the 5th of December. So let me go do that. And it depends on, Project 3 depends on this chapter, chapter 17, and that's it. So that is why we're doing it. I might as well get it to you now if you would like to get started. It's a chapter that is definitely worth reading. It's a very important one and cool. So let me release Project 3. I said December 5th. That is the last day of classes, right? Academic calendar. Let me just confirm that. Yeah, the final exams week starts the 8th, so we're doing it 5th. We're on the right track. So before I forget, let me just mark it as available and due. It'll be December 5th, the Friday, 5 p.m., the very last moment that it could possibly be due. That's when it will be due. All right? That's Project 3. It's based on Chapter 17. It's wonderful. All right? I think you'll enjoy it. Again, you can work in pairs if you would like for projects. Whee! So there's that one. It's ready. And yeah, it depends on this chapter, so just get started early if you would like. Read it sooner than I can teach it if you would like, but there's plenty of time. All right. So with that in mind, let's talk about prediction again. All right. So we'd like to predict the value of something. In this case, now it's going to be categorical. That's going to be the new thing. All right. So we're pros at regression now. We know the pros and cons. We know all the things we can do. We can generate a confidence interval. It's wonderful. Remember that the whole idea of predicting the value of something is you've got a data set. You assume that kind of matches your population decently well, and you don't have the full information, right? You don't have the full story. It's always based on incomplete information. You do not have a census. You just have a sample, right? And so we would like to use our best knowledge that we can glean from that information that we have from our sample to try to predict the values of people who come along later. All right, that's the goal. We want to figure out ways of predicting a new output given a new input that looks like our data set, all right, given the same kinds of rows and columns. So yeah, we originally learned this way, and this is going to come back again this time in this chapter. It's going to be a highlight of this chapter for categorical stuff. But one very easy way to make a prediction for somebody you haven't seen before is it's called nearest neighbor prediction. And that's going to be very important today. So like you've got your data set. Here's your data set. And you've got somebody new. You want to use X's to predict Y's. You got somebody new, bless you. You got somebody new right here. Bless you again. And we're thinking that, all right, let's go and find all the people nearby that value and take the average, and that can be the Y from the X's. That's the prediction. So one way of making a prediction for some new individual is go and find people who are like that individual, who are kind of close to where they were in their X, and use that to predict their Y. Use their outcomes to make your prediction. That's called nearest neighbor. Go find their neighbors, knock on their door, interview them, and take the average or something. All right, so that's a prediction method that we know and love that kind of led us into regression. We're going to come back to that this chapter, all right, harder. And yeah, just the idea of regression was the next thing. It's just like that's when you're predicting numeric values. We learned to do that by finding like the best line that we could draw through things, but we also learned how to find the best parabola that we could draw through things, the best quadratic function. It's always regression comes down to minimizing like the root mean squared error, or at least that's what we know how to do so far. All right, of some function. Usually it was linear for us. That's what linear regression did for us. So it predicted numeric values by, for example, minimizing the root mean squared error. Okay. Enter the new topic of this chapter. It's called classification. All right. Classification is we would like to predict not just like height of a child or something. We would like to predict categorical values like red, orange, yellow, green, blue, purple, something that has no number associated with it. We like to classify things. Here are some very, very early and important examples of classification problems. So you have a spam filter on your email, most likely, right? And so Google, if you have a Gmail account, for example, they're running and they're marking things as spam for you, aren't they? They're putting it in your spam folder already. And so they have a classification engine that's taking the text of your emails and outputting a categorical variable, isn't it? Spam or not spam. There's no numbers there, right? It's a categorical thing. So that's classification in a nutshell. It's like take an email's text, output whether or not it's spam or not spam. That is a classification problem because we are predicting a categorical thing. It's like, is it this thing or is it this thing? Does that make sense to us? That's the difference. That's the new thing, right? You could make this arbitrarily cool and difficult. Self-driving cars are classification problems. If you think about it. This is like a window into a self-driving car, what it sees in terms of all of its radar and things and its vision. What do you need to do if you're a self-driving car? You better be figuring out where the line of the road is, right? You better be figuring out where all the cars are, where all the stop signs are, everything that you need to deal with. Drawing boxes around pedestrians. So your input is pixels, perhaps, or radar data, and your output for each pixel, maybe, because you need to know, like, all these pixels over here are part of a stop sign. They come together or something. Your output is like, okay, here's another car. Here, this pixel represents part of the road. This pixel is just a tree. We don't want to run into that, right? Where's the sky? Because the sky is not the same as another car. We're never going to drive into that accidentally. Which pixels are part of traffic signs? And you want to, obviously there's more to it, but it's a classification problem. Does that make sense? You're predicting categorical things like, oh, that's a stop sign. There's no number associated with a stop sign, right? It's a categorical thing. And so hardcore machine learning, self-driving cars, for example, are solving classification problems. If you can do that well, you can make a car drive. Okay? That's the answer. So here's one last image that's moving this time, but like if you want to make an umpire for like tennis or some other game that has AI again, you just have like again maybe a camera pointed down, and so the input's pixels again, all the pixels that the camera sees, and then it tries to like find the ball, and its output, the classification problem again, is like, was the ball in or was the ball out, right? There's no number associated with that. It is a categorical thing. So classification is a huge deal, especially in machine learning, and data science is pretty much just a buzzword. It's the same thing, more or less. You would learn machine learning stuff if you became a data science major and went to a four-year college. Okay, so we need to learn then how to do this stuff. I've been saying that word just to make sure we're all on the same page. So like machine learning and data science, they do kind of go hand in hand. It's more or less the same ideas, but the technical details may be slightly different if you go look it up on Wikipedia. So machine learning is the idea of having a computer learn things like without your help. So machine learning, there's a bunch of different algorithms that have a computer learn things, but machine learning algorithms, they are mathematical models. So it's like you're making a black box that you don't fully understand a lot of the time. That's how like we don't fully understand why ChatGPT gives back the things that it does, but we have some thoughts about it, right? So machine learning is like you're building this thing, complicated black box that takes inputs and produces outputs. That's all you're doing, all right? You feed it inputs, it produces outputs, and it's doing some weird math deep in there that you can't fully understand. All right, if it's like a neural network, for example, if you've heard of that. So yeah, it's a machine learning algorithm generates some mathematical models that you create using sample data. So like you've taken your samples, it's still like data science at the end of the day. You've got some sample data and you want to make either predictions about that data or decisions based on that data. Like if you're a self-driving car, it's a decision time, right? Without actually programming what a stop sign is, without actually telling your self-driving car what does it mean for a double yellow line to be on the road. Like it can figure that out eventually if you give it enough data. That's the idea, right? To perform some task. So it learns on its own. There's algorithms that you feed it inputs and like you label, like there was a line here. Remember that. It can start noticing those lines. Like here's a stop sign. It can start noticing the stop signs. And it just kind of does it on its own. All right, that's machine learning. And so when you give sample data, like you give a bunch of pictures of stop signs, for example, to your self-driving car, there's a stop sign. Here's another picture that you give it of a stop sign, like way over here. Boop. Stop sign. A bunch of stop sign pictures, for example, in a bunch of different orientations and places. They're all saying stop. When you give it a bunch of labeled data like this, it's like, there is a stop sign in this picture, go find it. And here it is, like draw the box manually, You give labeled stuff that you've solved the problem for to your machine learning algorithm, and then it kind of learns what a stop sign is. That's kind of the general idea. So when you give it sample data like this, you give it a bunch of pictures of stop signs and also not stop signs. Like you give it a picture of a cloud. You give it a picture of a rainbow. Something like that. It needs to learn the difference, right? And you don't explicitly tell it what the difference is. You just like, here are pictures with stop signs. Here are pictures of not stop signs. Go figure it out. That's what machine learning is all about. It like kind of does it for you. So that's kind of where I want to stop with that line of thought. There, it gets very complicated, okay? And you can learn more about it, and I'd be happy to help you, but it's not part of this class. So in general, when you have a bunch of sample data like this, like you don't have the car out driving it, you're just trying to teach it these things, having it learn, the sample data is not called like a data set anymore. It's called your training data. Like you're having it go and, I don't know, you're having it work hard by itself. You're having it train itself for prime time. All right, that's going to be a word that we talk about a lot. Training data, and then there's also going to be test data. You're going to make sure that your machine learning model learned well by testing it on stuff it hasn't seen yet. That's going to be the goal. All right. Are there any questions so far? Just this is a little vague, but I hope you see the idea. Like, we would like to predict categorical variables. That's very important to us in the real world with things we'd like to do. And that leads to the idea of machine learning. All right. So we'd like to make a classifier, something that you feed it inputs, it classifies the output, in or out. Stop sign, green traffic light, red traffic light, spam, not spam. We'd like to make a classifier. All right. So that's our goal. And here's kind of how it works. You've already done this part. We understand this part. That's old stuff. This is new stuff, all right? Old stuff. And just using it in this way is kind of new, though. This is new stuff. This is what we're about to do. So the goal of a classifier is you give it a bunch of stuff, a bunch of attributes of this new thing, like here are the pixels of the image, here is the height of the child, or the height of the father and the height of the mother or something, and it's going to output something for you, all right? I guess I shouldn't have said height of father, height of mother. I should have said something like, here are the pixels of the image, was the ball in or out? Like, because it's classification. It's going to be predicting, was this thing, which categorical output was the thing. So yeah, that's what's happening. And the way that we get there, the way that we make our classifier work, the way that we train it is, again, we still have a population. Like, what is a good example that I'd like to use right now? Let's focus on, I guess I already drew these pictures. Let's focus on detecting a stop sign and drawing a box around the stop sign. Like, you're gonna feed in images, you're gonna make some data, your training data, your data total is pictures of stop signs and pictures of not stop signs. But the population that you're taking that from is just like every picture that you could ever take in the universe. Does that kind of make sense? Like, because you want your camera of your self-driving car to be looking at everything that it could possibly look at. It needs to be able to recognize anything ever. Does that make sense? So like your population that you want to take sample data from is anywhere that you could face a car in the universe. Yes? Even in space, perhaps. But you've taken only a few pictures from a car, right? That's your sample. You've taken a little sample, and then you've labeled that sample. Like, oh, we've got this one was a stop sign. This one was not a stop sign. Stuff like that. If you're trying to teach an image recognition classifier to find stop signs or not, you're gonna have a bunch of pictures that are of the road of a place that cars drive, and you're going to label it. You're going to manually say, oh yeah, this was a picture, here's a stop sign in it, this was a picture without a stop sign, and you're going to try to teach it the difference by telling it which one is which. All right, so you have that data, like you've got the images themselves, and you've got whether or not they're stop signs, something like that. And then the new thing that you do to train your classifier is you worked very hard on this data. You worked very hard. It cost you a lot of money. You do not have a way to like get more very easily. And so you're going to chop even that data in half now, or in third, in like 2/3, 1/3 or something. You're going to chop it in a way that you use some of it as training data. That's the stuff that you're going to train your classifier on. You're going to give it just those pictures and just those ones where it's like there was a stop sign here, there was not a stop sign here. And then you're going to hide away some of your data. You're going to use the training data to build your model, to build your little black box. And you're going to leave some of your testing data secretly to the side. Does that make sense? Because you want to test later, did the model that I made from my training data, does it do well on other things that it has not been trained on? Does that make sense? Because that would indicate that it like learned well about things in the world. Learned well about what a stop sign is. It didn't just like memorize the pictures that you gave it. Does that kind of make sense? That's what we want. And so we're going to cut a little bit of our data off and save it for later so that we can test the model that we made, test the classifier that we made. Does that kind of make a little bit of sense? So yeah, questions about that. So that's the new idea. You're still taking data, but you're going to cut it up and you're going to train your model on some of it. Train your classifier, let's say, on some of it. That's your black box. And then you're going to test it on some of it later. And you're only going to give it the pictures. Does that make sense? You're only going to give it the pictures here. You're not going to tell it was it a stop sign or not. You're going to see if it matches. You're going to see if it knew that that one in my test data set was a stop sign. You're going to see how it predicted from the model that you made, from the classifier that you made. So an example is worth 1,000 words. Are we ready for that example? Any questions first? I'll try to tell you about this process. All right. Let's do it. So, let me make a new section for this. Is like we're going to just manually make a classification function, something that you give it some data, it classifies it just manually based on things that we've discovered. Usually you're not going to want to do things manually, you're going to want to do it automatically, but this is a good start. All right, so let's make a manual classifier. So let's manually explore the data, exploring the data and creating a classification function. That's going to take in the inputs and output yes or no, essentially. That's my example. So I'm going to read in a table.read table. Here, our example is going to be ckd.csv, if you want to import that. ckd stands for, it stands for an illness. It stands for, CKD is short for chronic kidney disease, unfortunately. And there is apparently a long named table. So here, let me just show you some of this. ckd.sample, show me 5 of them, something like that. So here's what the CKD dataset looks like. You've got a bunch of people that either had or did not have chronic kidney disease. And here's some information about, like, I guess, a blood sample that was taken on them, I believe. Something like here is their blood pressure, like a doctor's visit or something. And here's a bunch of information. Maybe they also took blood. Here's their blood pressure. They looked at the cells under their microscope. They found some things, blood glucose random, all these different numbers associated with the values, as well as categorical things. Did they have hypertension? Did they have diabetes? And then at the very end here is the class. And the class is going to be 0 for they did not have chronic kidney disease, and 1 for they did have chronic kidney disease. Does that make sense? We are going to create a classifier that, given everything other than this, of course, because that would be cheating to have this too. Our job is to generate this, to tell, given all this other information about the patient, do they have chronic kidney disease? That would be very helpful for doctors, right? That's what we want. So let's go there. Let's change. Apparently the book changed blood glucose random to just glucose, because we're going to use that one. So I'll say relabeled. Take that one and change it to just glucose. So there, all this changes that. And there's some stuff again. So some new patients, I guess it's sampling, just to show you all the different things. So some of them were, sometimes it's class 0, sometimes it's class 1. Did they have chronic kidney disease? Did they not? We want to learn the difference. Does that make sense? That's what we'd like to do. That's very useful. So here, let's play this game. All right, we've got a data set. We started here essentially. We got all the attributes of information about their blood and their diabetes history and things like that. And then the labels are the classes. Does that make sense? It's the class. We're calling it class here. Class. And this is everything other than class. Everything other than class, class. And it's either 1 if they had chronic kidney disease and 0 if they did not have it. Okay? That's what's there. And so we would like to make a training set and a test set. We're going to look at the training set just manually this time and come up with a classification function that works well for that training data. And then we're going to test and see if what we came up with works well on the test data that we hid away from ourselves. Does that make sense? That's what we want. Because assuming new people, we get new patients, we're pretending that we got some new patients essentially with the test set and making sure that what we generated did the right thing for them too. So that's the strategy. That's the setup. So let's chop our data set in half. All right. Let's chop our data set in half. So let's also randomly place some things in the training set, not some things in the test set. Don't do it in the exact order. Don't chop it off at a certain point. Let's shuffle all the rows. So we can do that quite easily by taking a sample without replacement. So I say ckd.sample, and just by default it takes, if I did this right, it would take a sample of the same number of people with replacement. That would be a bootstrap sample. I would just like to shuffle who are there, all the people that are there right now. And so I'll just say with replacement. So still take just as many, but with replacement equals false, to just keep just as many people and just reorder those original people. Shuffled ckd is that. And next we want to take half and half. So we need to know how many rows are in either of the data sets, ckd number, shuffled ckd will have the same number of rows. So there's apparently 158 of these people. So we don't have to chop it in exactly half. Sometimes you use more training data than test data. So let's just let's take the first 100 of the shuffled stuff, and that can be our training data, and then our test data can be everything else. So training set can be the shuffled stuff, and then I take the first 100. And remember that you can use the take operation on a table to do that. You give it an array of all the indices that you would like to take out and pick out. So the np.arange will pick out indices 0, 1, 2, 3, all the way to 99. So the first 100. And so take just those for the training set. And then for the test set, take everybody else. So from index 100 onwards, right? Because this one would go up to index 99. So start at 100 and go all the way to 157, because it would start at index 0, right? 0 to 157. So up to 158, but not including it. So that would be the training set and the test set. Does that make sense? I've split it up there. So I've got 2 different tables now. One with 100 things, one with, I guess, 58 things. And we can see who's where. We can do a group, right? We can see our training set looks like this. There's a bunch of shuffled stuff. and there's exactly 100 things. Some of them are class 1. It looks like more of them are class 0, so I guess more people in the universe don't have CKD, chronic kidney disease. We can see like what's in our training set. Training set dot group. We can group by class. It's like it looks like there were about 70 is like 70-30 split, more or less, of people who didn't have CKD and people who did have CKD, chronic kidney disease. And so we can do a scatter plot of some numeric variables and some that correlate well with whether there is CKD and or not CKD are the, I don't know what the units of any of this are in by the way, but apparently glucose and hemoglobin. I think that's how you pronounce that, right? Please correct me if I'm not saying that right. Glucose and hemoglobin. Those two, like you can use those to kind of predict well whether or not somebody has chronic kidney disease. So let's do that. Training. We're looking at our training set. We are not inspecting the test set. That's secret. We have to come up with our classification function first, and then we can test it later on the secret stuff that we've hidden away. So let's do a scatter plot of hemoglobin and glucose. And that would just give you a bunch of dots. There's a cool thing that you can do to a scatter plot, and I don't know if I've shown you this already. I don't actually know if it's in here. It's not even documented. It's secret. If you say group equals something, it will color things based on what you have there. Group by the class label. Watch what that means. It's going to split up the data into, was it class 0 or was it class 1, the things that it's plotting here. It's still plotting hemoglobin and glucose on the Y, but it split up the stuff that was class 0, the people who did not have CKD, and the people who did. And do you see that there's a decent cutoff right there? So it looks like all the people who did not have chronic kidney disease, they had hemoglobin like above 13-ish, and they had glucose below like 125-ish. Does that kind of make sense? So that could be our classifier. Like, is your dot here? You give me hemoglobin and glucose for a new patient. Is the dot here? If so, class 0. Is it anywhere else? Class 1. See how that could be a classifier? That's something we could manually make. All right. So let's see. How do I want to do that? So let's find like what is that true minimum value? Let's cut it off exactly. What is that true minimum hemoglobin value? For class 0 is, all right, let's go into the training set and get all the stuff where the class values are equal to 0 and get me the column for those class 0 people called hemoglobin and get me I can do a dot and min on that actually. So that I can do that. And I can also do the same thing for, what was it, glucose. I can get the maximum glucose. Like, don't go above that one for class 0, right? Give me the maximum for that one. Oop. So I can say max glucose for class 0. That's going to be, oh good, gosh, I pressed a button. Max glucose for class 0. That's going to be go where it's class 0, get me the glucose column. Give me all the people who are class 0, give me their glucose values, and give me the maximum one. Because that's a good cutoff for me. And if I can print them both out together by putting a comma. It's like, here's the min hemoglobin, here's the max glucose. Boop. And it looks like it was exactly 13 for hemoglobin, and the cutoff was 140 glucose units, whatever that is. So that can be a classifier. If you give me a hemoglobin value and you give me a glucose value for a brand new patient, you can just see like if it's within that square, within that rectangle. If it is class 0, otherwise class 1. Does that kind of make sense? How you could classify based on that data? So using those exact values, how about you try? There's time for you to try this. Here's what I want. Try this. Fresh dice. I'll give you a few minutes head start. Try to create, we want a function. Create a function because we can apply that function, right? Create a function called, I guess let's call it classify manually, because we're manually classifying stuff. That takes two things. That takes one hemoglobin value and one glucose value. and glucose values, and returns a classification of 1 or 0 based on those values. So essentially you kind of want to call it like this, like classify manually. If I called it with like 15 and, I don't know, 100, that would put me like here and here. You should say class, you should give back a 0 for that call. Does that kind of make sense? That's what you want. But if I said, I don't know, classify manually 10 and like 300, that one would be for hemoglobin and glucose. 10, 300, that would be over here. Like you should say that's a 1 because it's outside of that rectangle. Does that make sense? So try to make a function that like this one gives back a 0, this one gives back a 1. Make a function called classify manually based on this min value and max value that kind of cuts off what's where. Can I show you all that at once? Yeah. Does that make sense? So try to do that. You're going to need an if statement, right? An if else. Maybe an elif, depending on how you want to do it. But try to do that. Try to figure out like where the inputs, the values, the first one can be for hemoglobin, the second one can be for glucose. Were those values within that rectangle or were they outside of it? See how that could be an if else perhaps? Maybe an if else. I'll give you a couple minutes. Let's start next. We'll see if you can wrangle the ideas together. Say death, classify manually. And then hemoglobin can come around to it or something. But that will get us all the way down to all right, that is my timer. Any questions before I show you how I might think about it? Did you do it? Did it work for these calls? Let's see. So def, classify manually. What do we get? You give me a hemoglobin value. You could call this X and Y, doesn't matter. But like the first thing can be the hemoglobin value, the second thing can be the glucose value for this new patient that you haven't seen yet. You want to classify them. See, like predict whether or not they're going to be, they're going to have chronic kidney disease or not. 0 for they did not, 1 for they did. That's just how people do that kind of stuff. So we would like to make sure that it's like within here and here, right? So there's a couple ways to do it with your current knowledge. Depending on, actually, does your book, when you guys read about the if else statements, did it teach you or and and? Did it say those words? because that could fix it. That could make this easier for us. So like we're within this range if like we're within the blue dot range if the if like the hemoglobin value is at least 13, right? If hemoglobin is bigger than or equal to 13, which is the min hemoglobin for 0, and the value for glucose is smaller than the maximum glucose for 0. And glucose value that you gave me was smaller than or equal to the max glucose for 0. Does this word "and" make sense to us when I put it there? Did we read about that? So yeah, if both of those are true at once, then return 0. Does that make sense? And then the else kind of makes it easy. It's just like if that wasn't true, that means it was not within that rectangle, which means we can return 1. Yeah, something like that. So that can be our input. Like if hemoglobin is bigger than or equal to 13, so the hemoglobin is like from here onward to infinity, and the glucose is from here downward to negative infinity, that'll just like cut off this part of the graph for us. Only take those things, and that's perfect. Boop. And so this one will say 0, this one will say 1, and we got ourselves a classifier. So that kind of makes sense. You give it stuff, you give it hemoglobin and glucose, it predicts the class. So you don't give it the class, obviously that would be cheating. So that's how that works. And what we can do now is we can see how well it did, because we saved away a test set, didn't we? We have not looked at the test set. We have not yet looked at it. But you can imagine the inputs and outputs look the same. The values kind of are similar. So let's take our test set. Let's select out just the hemoglobin and glucose, because that's all we need. All right. So there's the test set. Those are our inputs, right? For this one, try our function. For this one, try our function. Try to predict, try to classify the test set. Yeah? That's how we're training. We trained. We made our model. Let's test our model. Test our classifier. Okay? So take that and apply it to the apply the classify manually function to that column 0 and 1. Hemoglobin, then glucose. I don't want to type them out again. That will give me all these. So it looked like the first thing in the test set it thought was not CKD. It thought that the second patient also didn't have CKD. It thought that the third patient did, though. See how it's doing that? So it's coming up with those thoughts. And you better believe we also have the test set labeled, right? The test set, it also has a class column of the actual data for that patient. Like, did they really have CKD or not? So we can go and get that column, right? Dot column class. We can go and get that, right? And we need to compare the two. Does that make sense? We want to compare the two of these. Did our predictions match what actually happened? So we can do a double equals. Like, was that equal to the actual stuff that we saw? Does that idea make sense? We can check that. And these are, like, we want to see if that's true. And we can call these, by the way, this application. Those are our classifications. We can call that our classifications. And so that makes this a bit short. It's like, were the classifications equal to the actual classes? And it looks like it's a bunch of trues, right? You can check and see like how many trues there were total. So like you can say, give me, do this. Looks like there's a bunch of trues. We can take, Python NumPy knows that true means 1, false means 0. So we can take the average how many trues there were. There were 100% trues. And by true, we mean they matched perfectly. So our classifier was 100% accurate for our test data. That's a decent classifier, even though we made it manually. Does that make sense? So I'm sure people noticed this a long time ago. This is nothing new. But do you see how this could really help doctors? If you had all this data, you can just like run our classifier, and send an email to the patients. Go get them if this was like a checkup thing, you can immediately flag the ones who, if they hadn't been tested for CKD yet, you can tell them, yes, you should go get tested. We need to keep you healthy. Or was that a hand or anything? No. All right. So that's lovely. 100% accuracy for a manual classifier. We would like to do this with a little less thought, though. That's our goal. So we're going to learn some standard methods of doing that more easily, more efficiently than just staring at the data, because sometimes you can't just stare at the data, all right? Often, 2 dimensions, like this is x's and y's, give me 2 things, I'll give you an output. Like that's easy for us to visualize. That's usually never useful enough in the real world. Let me show you an example where 2 dimensions is not enough. Sometimes 2 dimensions isn't enough. Dun, dun, dun. And that gets much harder to visualize. You can do 3 maybe, make a 3D graph, but you got 4 attributes predicting a class, things are not going to look well for you, all right? So here is a fun example of stuff. I will just copy and paste this from here, because there's way too much going on today. Sorry if I go back and forth a lot. It's just like there's a million things that you don't need to fully understand that I need to type here. It's like read the table. You know how to read a table. So here's a table about banknotes, so like dollar bills or something. And the classes here, let me shuffle it. Give me a sample. Some of the classes are 1, some of the classes are 0, and I believe that 0 means not counterfeit and 1 means they were counterfeit. So somebody was breaking the law and creating fake $100 bills or something. And here's all the information about that dollar bill, about that banknote that was either counterfeit or not counterfeit, I believe. And so got some interesting information about it, I think from like image processing algorithms. I don't fully understand what that means. But we can see like how many of our data was banknotes.group. Let's group by class again. We got about equal amounts of non-counterfeit and counterfeit data. So what you would want to do right now is if you're going to train a classifier and do something, you would want to split it off into training data and test data. But I just want to show you, it's not even doing that. I just want to show you that two dimensions is not enough to deal with this data set and try to predict counterfeit or not counterfeit. Because if you picked 2, if you picked like wavelet skew and entropy, for example, and you did a scatter plot, so banknotes, scatter, whatever in the world that is, and whatever entropy is. I think it's image processing output stuff. And you say group equals class, which is kind of cool. You can color it different depending on the class. Do you see how there's a ton of overlap? So even though we know that, okay, for sure these over here are counterfeits, there's a lot of overlap in the middle here. And so you would not have any use in making a classifier based on these 2 values, because like you would be wrong a whole lot in this area. Yeah, it's not good enough. So same with with another combination of 2. If we did wavelet var, or whatever that is, and wavelet hurt, whatever that is. Again, you have the same issue. It's like, all right, we can see some outliers, and like we can kind of draw a line maybe here and have a decent prediction engine, classification engine, but you're again going to be wrong a whole lot. That's not good enough. It's not good enough to just take 2 things. But if you combined more than 2, dun, 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 if I did this, and you do not need to understand how to do this. You can make a 3D graph, and this is, I'm graphing wavelet skew, wavelet var, and wavelet curt. And I guess this is the x-axis, this is the y-axis, this is the z-axis. In 3 dimensions, if I move this graph, there is a clear separation there. You see that? So you can use, I guess with 3 dimensions, you can make a little separating plane. You cannot make a little separating line in 2 dimensions. That's kind of neat. And that's going to be the moral of the story for the rest of the examples in this chapter. It's going to be like, we have 17 numerical data points per individual. We have 17 labels and then a class. So essentially, we want to draw like a 17D line between class 1 and class 0. Does that kind of make sense? It's very hard to visualize, but that's what we'd like to do. We would like to handle just like multiple dimensions, because the more data you have, you should be using it all at once, right? That would help with your classification. You don't want to throw things away if it could help you. That will make you more accurate. So are there any questions about that? Does that make enough sense? That is our goal, and that's where we're going. So we want to make this box kind of in some cookie cutter way that we don't have to really look at the data very, very closely, and that's going to work quite often. And it's going to come back to this idea of nearest neighbor. I will show you what that means. Are you ready for it? All right, you see how very technical and weird this chapter is. It's very different, but it's a lot of combinations of stuff we know. I'll show you that. So the classification method that I want to teach you, that the book is going to talk about in this chapter, is called nearest neighbors. All right, the nearest neighbor classifier, where it is going to be the same idea of you give me an input, I will go find similar inputs and like figure out somehow the categorical class output answer based on what I see nearby. That's what's going to happen. So it's not going to be numbers. You can't like take the average. It's just like go and find the things nearby. Were they class 1 or were they class 0? Something like that. And we're going to end up using like, we're going to have them all vote and take majority rule. That's how it's going to work. All right. But that's what's called the nearest neighbor classifier. What's going to happen is we're going to go and find the most similar training examples, because we're always training with our training set, right? That's all we get to generate our model and see if it worked out, right? I'm going to use that to generate our model, see if it worked out, and we're gonna give pieces, purple pieces of, you can think about it that way. We're going to give little purple pieces of the test set to our model, and it will spit out little green pieces. It will spit out labels, class 1 or class 0. And we can see if it worked or not based on that, how often it did it right. Okay, so that's always the goal. And this used to be what color? Blue. So that's the goal. That's what's going to happen. And the way it works is, yeah, it's always the idea of your classifier is being trained to like take labels, everything but the class, right? Everything but the class. Take everything else, all the numerical stuff, all the categorical stuff, if you can figure out how. Take all those things, all those attributes that were not the label, not the class, feed them into the classifier that goes and finds all of the other training examples. So go find like, all right, in the training set, there's this one, and this one that are most similar. Let's go look at their classes. Some are going to be 1, some of them are going to be 0, right? Go and find what they were. Maybe it was like 1, 1, 0 or something, and let majority rule. If it was 1, 1, 0, we should predict 1 then. Does that kind of make sense? If the most similar 3 1s in our training data for this new thing coming out of the test set, or some new person that's like from the real world, if the most similar 3 things were 1, 1, 0 or something, the most similar things that look like this one were like 1, 1, 0 in the class, we should predict 1. We take majority rule. It won't always agree every time, but it's going to be pretty good. We're going to let them battle it out among each other. So you should always find an odd number then of similar training examples. The simplest one is to just use the most similar training example. Just go and find 1. What class was that one? Okay, that's the class that I'm going to predict for this new thing. I know that's a lot of words, but I hope that the diagram somehow helps at least a little bit. Are there any questions about that idea of nearest neighbor classifier? You give me a point in some multi-dimensional space. Like here's all my data. Imagine it's in a 17-dimensional space. You give me a new point that's like right here. I'm going to go find similar ones around that and look at their class. And I'm going to see which ones they were, which classes they were, and the class that wins out, the one that had more, that's my prediction for this new person, for this new dot in the space. That make a little bit of sense? So yeah, it's just like, think of it as some weird graph, and you're finding, like, you're drawing a sphere around those points that you see. That's nearest neighbor in a nutshell. All right? And that was some great alliteration. All right. Are you ready for an example of that? You'll draw some more pictures. It's pre-made. It's very involved. You don't have to understand any of the code that I'm about to write, that I'm about to paste. All right? So just let me paste it. It's going to take a second. But this is, and just yell at me if you have any questions. Here's my actual notebook. So pre-made nearest neighbor classifier example. And we're going to just use the one most similar training example, I believe. Let me make sure of that before I say the wrong thing. Is that what's happening here? Classified 1. I think, yeah, classified grade 1. All right, we're just going to find the one most similar one. So we're going to, I'm going to say a word, and it's going to make sense soon. Classify example with k equals 1. K just kind of means how many things are we using in our classification? How many closest things are we finding? Just the one closest thing. That's what that means. And so now let me paste in a million lines of code. Whee! Don't worry about any of this. We're going to write it ourselves later. There's that. Here is a ridiculous amount of code with functions. Some of them you know, like standard units. We know how to do that one. The rest you probably don't. So let's just change the plot back to like 2D and normal, where I can't use my mouse. But here's a bunch of stuff. Don't worry about it. And let's read in the CKD table again and do something to it. Don't worry about what we're doing to it. We'll get there eventually. But here's the CKD table. It's doing some stuff to it. Just picking out the things that we care about. Let's deal with hemoglobin, glucose, and white blood cell count. All right, and then here's the class. Was it 0? Was it 1? Sometimes it was, sometimes it wasn't. I should really be splitting up into training and test data. We're just going to use the whole thing as the training data. It's fine. Just for the sake of what we're doing here. So we know, let's see here. We know that there's a nice cutoff for just 2 dimensions for hemoglobin and glucose. Yeah, it does that sometimes. Boop. For just hemoglobin and glucose, this is the entire training data. We know there's a cutoff right there. The units have been changed to standard units. Don't worry about it. It's been squished a little bit. The whole idea of if this is our classifier and like you're using this to section off your stuff, what we will do, the way that nearest neighbors works in general, we're going to go find the most similar one for you. Give me a new dot. You give me a new dot for a new patient. You give me their hemoglobin values. You give me their glucose values. I will go and find for you the nearest patient in my training data. And that's the one I'm going to use to predict. All right. So let's say we've got a new person A, and in computer science and data science, instead of person A, they always give them a real name. They're like, person A, we're going to call them Alice. Person B, we're going to call them Bob. Person C, we're going to call them Charlie. Like, it's a thing. So like, let's say Alice comes along. She's our new patient. And we're going to say that her hemoglobin value was 0 and her glucose value is 0.95. The way that nearest neighbors works, the second we have a patient, a new dot, right? We're going to draw the dot. It's like 0.95. So there, maybe about there. So she's like right here. Yeah, that's our new dot. We're going to go and find the nearest dot in our training data closest to Alice. That's what nearest neighbor is all about. You go and find at least one of the closest things next to Alice. So that's this. It's a cute little picture. So here's Alice, and apparently the closest thing to Alice was not this one. This one was a little bit closer. That makes sense? Just a little bit. And so, therefore, we would predict for this Alice character that she was going to be not having CKD. Does that make sense? We're probably going to be wrong. We're going to be wrong for like this edge, probably. But that's what nearest neighbor is all about. If you had more, you go find more dots. You'd probably find like these guys or something. And then maybe the ones would win out against the zeros. But that's nearest neighbors in a nutshell. You go find the closest dots to the new dot and see what classes they were, let majority rule. If you're just finding one, it's like, that's the closest one, predict whatever that one's class was. Okay? Questions about that? You see how it's all kind of coming together, how that works like this? Use the label of the most similar training examples, potentially plural. All right? This is just singular right now. So let me show you, like, let's pretend we got a bunch of new dots. Let's try to visualize what's going to happen. Like, we have a new patient here, we have a new patient here, a new patient here. Like, let's draw a million dots and see what nearest neighbor is for just one. Go find the nearest one person. Use that as the prediction. Let's see how that classifier looks. So here's just interesting examples. This is just making a bunch of people, a bunch of sample people. And so here's a bunch of new dots. We're going to make them in red for now. But here are the dots. So I'm going to change the colors of these dots now. I'm like, for this person, I'm going to go find the nearest person in the data set and color it based on their class. Was it class 0? Color in blue. Was it class 1? Was that the closest thing? I'll color in yellow. And we'll see like the cutoff. It's going to look like that. But we can have it here too. It'll take a little second because it takes a while. Don't worry about it. Because it's got to do the classification for a few hundred dots, right? And so here's like the frontier, the range. It looks like for right here, the closest dot is still blue. For this new patient, right, if you had one right here, but over here, if you went a little bit farther, looks like the closest dot is now the yellow one. Something like that. It's like that's going to be like, you give me a dot here, I'll go find the nearest neighbor to that one in our training set and color them the same. Give them the same class that we thought was the closest one. All right, and so that's how it's going to predict. You can imagine it's probably going to be wrong around here sometimes, but that's what it means to do nearest neighbor. Does that make sense? That's less thought. Just like you'll find the nearest thing, call it that. That's how it's going to work. Let's see. Any questions about that? Yeah, that's how that's going to work. What else was I going to say? This makes false. We can do I want to do any sort of values again? Because now the idea would be to do some sort of evaluation of this. Like what was make a training set, make a test set, do what it's going to look like and see what happens. So that would be the goal later, but that's in picture form what nearest neighbors is all about. All right. So if that makes enough sense, do yell at me. I'd like to teach you how to do that, like how to actually write the code that makes that happen. Are we ready for that? Because it's going to be quite involved, I think you can imagine. It's going to take some thought and some time. We might not finish it this lecture, but we'll get to it. And we're just going to practice from then on. Okay? So let's make it happen. So here is the full name of the algorithm. It's not just called nearest neighbors. The one that I want to teach is called the K nearest neighbors algorithm. All right. And so we say KNN for short, where there's a dash there for fun. So we're going to find the K nearest neighbors for every new dot and use those to predict and to classify the categorical output variable for that new dot that you find. All right. So here's the goal. Here's the algorithm. It's called K nearest neighbors, where you pick the value of a K. I just showed you this example here was where K was 1. All right, so that example was where K was 1, and that's why I wrote that right there. Now you know. So if you just choose and find the 1 nearest neighbor, the closest one, that's where it's 1 nearest neighbor. But you can make 3 nearest neighbor, 5 nearest neighbor. So you want to find the K nearest neighbors of some new sample point. Here's how you do it, right? You need to then go and find the distance, right, on the graph. Go find the distance between your new sample point and every other sample point in the training set, right? Every other individual, every other patient, whatever you got there. Go and find the distance between that one point and everybody else. Like here's your dots. Oh wait, let's start at blue. I like blue, just to be the default. Here are your dots. Here is, I don't know, here's your new dot. And you can imagine that if K was 3, you do that. You go find the 3 nearest neighbors to that new dot. Does that make sense? That's what you go and do. And the way you do that is you find the distance, from that dot to everybody in the data set. Find the dots. Distance from there to there to there, everybody in the data set. All the ones. And you want to find the 3 smallest distances. Yes? If K was 3. Does that kind of make sense? What's going to happen? You find those distances in mathematical distance land, and essentially what you can do is you have your training data, like it's already a table, right? It's got all the attributes, it's got the class name, just like add a new column called distance to this new dot. Just like make an extra column, like you got all these other things, boop, 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 including class, like add distance here. Distance to the green new dot, all right? To that brand new dot, shiny and new. And what you want to kind of do once you've got that, right, distance to the green dot, you want to take all these numbers and you want to sort them, right? Like 0.1 at the top, 0.2, 0.5, 1, 2, on and on and on, yeah? You want the like you want the 3 closest ones at the top, so you want to sort it, right? So you want to add the distance to that new dot to your training data, add a new column. You want to sort it in increasing order, and you take the top few rows, and you want to see what their class was. Were they all like, maybe it was 0, 1, 0, I'm not sure. Depending on what they were, then you let majority rule. Kind of. That kind of makes sense, the process. So you need to go and find the distance. You've got a new dot. Go and find the distance from that dot to everybody in the training set. Every single person. All of them. Make that a new column of your table, because it's already a table, right, for your training data. You want to find the smallest distances, so you're going to sort by distance. And then you also have the classes for those closest points, don't you? You're going to take the top few rows, and you're going to use the classes of those top few rows to make your prediction. You're going to have majority rule. All right? Is that clear enough? Does that make enough sense? That's most of the algorithm. Devil is in the details, of course. And then, yeah, you just kind of like, if k was 3, like, all right, the 3 closest ones have class 0, 1, and 0. 0 is more frequent, so I'll predict for this new dot that the class will be 0 for it. You let majority rule. So you should want to have an odd number for k, always. Otherwise, you can't break ties. You can't have class 0.5. Okay? Yeah, that's how that's going to work. And I hope that makes sense. Are we ready to kind of learn how to do that distance calculation? So that's the first step. Might as well learn that first. All right, so it goes back to math and like geometry. Do we remember the Pythagorean theorem? That's pretty much it. It's going to work for any arbitrary number of dimensions, but here's a two-dimensional example. Like you've got 2 points, right? You got x1, y1, you got x0, y0. You want to find the distance between the two. How do you get there? Well, the order actually doesn't matter because you're going to square it and the negatives go away. But it's like, all right, the bigger one was x1 and the smaller one is x0. Like, give me that distance, square it, right? Because that's like the width. That's x1 minus x0. That's y1 minus y0. You know that this distance, right, is going to be the hypotenuse of that triangle. So it's going to be, if this is a, this is b, this is c, right? You know that a squared plus b squared equals c squared. A, B, C equals a squared plus b squared. And then, c squared equals that. And so, of course, you're going to take the square root. So that's how you find that distance. It's just, all right, x1 minus x0 squared, y1 minus y0 squared, and then take the square root of all that, because we want the actual distance. So it's really just the hypotenuse of a triangle deep down, and maybe we remembered that already. So that's how you find the distance between 2 points, all right? And that's going to work for any arbitrary dimension, actually. If you had 3 dimensions, you like had a z as well as an x and a y. Like you just, the pattern keeps going. There's going to be no difference. There's a cool graphical proof that I do not fully know how to explain, but it's like you take what you had for the x's and the y's, you also just add the distance, like z1 minus z0 squared. And you keep going for the other ones too, like p1 minus p0 squared. Just like put it all in the square root, it'll all work out. That's how you find the distance in 3 dimensions, 4 dimensions, a million dimensions. All right, it's always the same. Just like take the corresponding coordinates, subtract them, square them, add them together, take the square root. Okay, so let's learn how to do that efficiently in code. I think that would be useful. Boop. So now this is nearest neighbors from scratch now. I guess it's k nearest neighbors. K nearest neighbors from scratch. Oops, this one's marked down. Boop. Yeah, so the first step is calculating distance. It's going to be a very long notebook, so I might as well section it off as well as I can. So let's read back in, because the example messed with our table. Let's read back in the stuff. We've got CKD equals this. Boop. And then it's also got a bunch of stuff by default. Let's just take the things that we care about. CKD equals CKD.select. Let's take hemoglobin, glucose, and the class, because we know that that's a decent way to specify. It's 2 dimensions is good enough for us for now. So there's the CKD table as we have just made it. We've taken the 3 things we care about. We would then want to go and split it up again into a training data set and a test data set, but let's pretend we've already done that and this whole thing is our training set, okay? So again, somebody comes along, some new person, and we want to do k nearest neighbors on them. We want to find the k nearest neighbors to some new person, Alice, that comes into the doctor's office and gets some tests done, all right? So the very first step is to find the distance between Alice and everybody in the training data set. Everybody, yeah? So here's Alice. Alice is, make array, her hemoglobin is 0, her glucose is 1.1 or something. I don't know. Something like that. There's Alice. And we would like the goal now, right? Here's Alice. Make her an array. X is the first thing, Y is the second thing. Or hemoglobin is the first thing, glucose is the second thing. For her now, goal is we want to find the distance from Alice to everyone in the data set. Yeah, we need that. From this person with hemoglobin 11.2 and glucose 117, how far away is that from Alice? How far away is this point from Alice? Yeah, how far away is this point from Alice? We do that. Yes, so that needs to happen. And so, all right, let's start with the first one. How do we get this first person? One way to do it is to do like ckd.drop the class, because we don't want the class, and give me row 0. Yeah, there it is. There's 11.2-ish and 117 on the glucose. See that? So there's the first person. We can get them like that. Get the row 0. That's like patient 1 in our training set. Patient 1 is that. And so I want to do this for everybody, but like the first step of the first step is find the distance between Alice and patient 1. There's X, there's Y, there's X, there's Y. Yeah? Let's do it. It's going to be a little weird, but by the way, the type of, when you get a row out, it's called row. What's the type of patient 1? Boop. It's a row. The type of Alice is array. Alice is a NumPy array. It would be easier if they were both the same, but you can still use the dot item on both of them. It will still work. So distance calculation. We've got x1 minus x1, x0 squared plus y1 minus y0 squared, and then you take the square root. Let's do it. Dun, dun, dun. How do I want to do that? Yeah, so we've got Alice can be x1s, and the patient 1 can be x0. So it's going to be like, take the x differences, Alice to item 0, so Alice is x, subtract it from patient 1's x to item 0, and square it, yeah? Does that make sense? So that's this first inner part, x1 minus x0 squared. So take the same items, item 0, those are the x parts. This one and this one. The order doesn't matter, because you're going to square it after you subtract. Do that, square it, and then do the same thing. You're going to add that to the y1 minus y0 squared. So it's going to be item 1's squared now. Item 1 squared. And then you just want to take the square root of all of that. Yeah? That's all of that. You take the square root. So one way to do that is like to the 0.5. There is our distance from patient 1 to Alice, or Alice to patient 1. This order doesn't matter. Does that kind of process make a little bit of sense? Like, that's what we gotta do for everybody, for all the people in this set. So like, we need to make a function, right? So we can apply that function. That would make our life so much easier. We could honestly make this calculation. This is also looking quite ugly. We could also make this faster if we could just have them both be arrays. There's a secret there. So if patient 1 was an array, this process could be faster. So I'm trying to motivate the final answer here. Because if patient 1 was an array, you could like subtract arrays and it would just subtract elements of those arrays. And that's kind of the first part, right? And then you square and then it all works out. So let me try to get you there. So sadly, you can't be like, make array patient 1. Really? Wait, never mind. I guess you can. I'm silly. For some reason, the book was like, no, you can't do that. Oh, wait, no, sorry, yes, I can't. This is now, you see how there's 2 brackets? It is wrong. It's an array of arrays right now. That's disgusting. You could do you could be like dot item 0. Oh, that's still also disgusting. But you see how when I do that, versus when I do and look at Alice. Do you see the difference? There's two square brackets versus a one square bracket. I think that messes everything up. So the way that you make patient one into an array, I think, can I say a star here? Yeah, I could do that. I can say star patient one. I don't want to teach you that part of Python. The answer is going to be just say np.array. There's a function in the NumPy library that takes something that could be an array but isn't and converts it. Make array does something slightly different. So like there, it'll do that. That's, yeah, make array doesn't quite work for conversion. That's the moral of that story. It's like, it's too nested. It makes an array of arrays, which we do not want. So that's how we can convert patient one into an array. And now I can do this process very easily because if I want to subtract the x1s and the y's, the x's from each other and the y's from each other, now I can say, give me Alice, and just subtract the array patient one. Do you see how that's going to make the array of their subtracted x's and their subtracted y's? That's lovely. That'll do it all. That'll do the first part for me. That's the subtracted x's and subtracted y's. And then I just need to square the subtracted x's and the subtracted y's, don't I? And then take the square root of the whole thing after I sum them together. So there's the first part, subtract the x's from the y's. That's the quick way to do it in NumPy land, in array land. Then we square those differences. You can again apply the squaring operation and just works on those arrays. So there they are squared. So that's the x difference is squared and the y difference is squared. I want to add them up and take the square root. That's what I want. So to add them up, you can do NumPy like dot sum. You do there's also NumPy dot sum. There's also just the function called sum. Any of the ways, do that. Sum them up, and then we just want the square root. We want the square root, and so to the 0.5 would also would finish it off. So that's less typing, and this is actually more generic. It's going to work for any dimension. So that's quite nice. That's lovely. So I think, how about you try it now? So here, let's have a function. This is Alice, this is make array. Try to make a function called distance. Create a distance function that like takes two things, like 0.1 and 0.2 function that returns the distance between 2 points that are represented as arrays. So we want to call it like this. We'd say, give me the distance, please, between Alice and the array version of patient 1. You want to call it like that, so Alice gets plopped into 0.1, this guy gets plopped into 0.2, and then it should give you back this exact answer. Does that kind of make sense? So give that a try. Let's see. Alice is 0, 1.1 if you need that, but try to make a distance function. I'll give you a couple minutes to give that a try. To like generalize, because that's the process. It's essentially copy and paste this, but like generalize what the two things are, the 2 points. I think that would be helpful. Because that's the very first step of doing nearest neighbors. We want distance from this new point, this Alice point, to everyone. And what we want to do is apply that distance function in a weirder way. There's always going to be the new point on the make another function and calls the distance function for us. That's the goal. We have that, we can apply it in some cool, weird way. I'm gonna put that in the fridge. We'll find out. That's my timer about to go off. Any questions before I show you the answer? Should it make enough sense what you want? You want two parameters, and they are both arrays, and you kind of want to generalize this process to return that distance back. So that'll be the very first thing you should say is def distance, right? And you can call the two things anyway, P1, P2, like give them some name that's useful to you, but I'll call them point 1 and point 2. And I want to return this process for those 2 points, where there's something, it's just point 1 and point 2 now. It's point 1's stuff, minus, like the very first things, you subtract the x's and the y's, or also the x's, y's, and z's of point 1 and point 2. Like, do you see how that generalizes to be like that? Yeah, so that should do it. And so if I call it, you better believe it returns the same answer because it's doing the same stuff. And now that's a function I can use for the rest of the chapter. Yeah, so that's lovely. I believe that's what I wanted to do there. Are there any questions about that? All right, we're getting to a good stopping point, I would say. So yeah, the next piece of the puzzle is, all right, we've done that. We've got the distances for everybody. Like how do we get our classifier working? We've got this top k rows. Like how do we use them? Like I was saying, and you're gonna let majority rule. All right, so to classify a point, let me draw that picture again. So you've got a bunch of points. Some of them are one class. Some of them are another class. Some of them look like that. And let's say you have, you got Alice now. We want to know where Alice lies here. So let's say, I don't know, that's the easiest place for me to draw a dot. There's Alice, all right? We want to classify Alice. So we want to find her k nearest neighbors. We want to go and find the distance from that new dot, that red dot or the rainbow dot, to every other point in the data set. All right, so like that one. Let's say that k is 3. So do you see how we're going to find the distance from her to everybody, and we're going to find those 3, right? Those 3 are for sure going to be the closest 3 in our data set. And we're going to look at their colors. We're going to look at their classes. Let's say that, I don't know, I'll just keep it generic, the blue class and the green class, yeah? So we've got, for Alice, we've got we've got a blue thing, we've got 2 blue things, and a green thing. Those are the k nearest neighbors where k was 3, yeah? We're going to let them vote now. We're going to take a majority vote of those k nearest neighbors, blue versus green, and we're going to see which of the 2 classes, for this example, for this chapter at least, we're going to assume there's only 2 classes to deal with. There's ways to generalize this to handle any other kind of class. Like maybe there's 3 or something. But you take a majority vote and you see which one appears more often, and like that's what you call Alice. And so the one that won the majority vote for us is the blue for this silly drawn out example. That's going to be blue for us, all right? And I hope you see why you want to use an odd k value. You cannot, if k was 4, you could have had 2 blues and 2 greens, and then what do you do? The question is, what do? You could be like, you can give up, I guess, say like, I don't know, need more information, but it's usually best to always have a real answer for everybody. So everybody's agreed that an odd k is the right way to do it, so that majority will always win out in some nice way. Yeah, and so with that, that's the process. Do the words make sense? Do the pictures make sense? Because all we need to do is turn that into code, and then we can make a function, right? That like you give me the training data, you give me the new point, you give me k. That's all you really need, right? Like eventually we're gonna make a function that looks like this. It's called k nearest neighbors. You give me all the training data because that's what we're looking at, right? As we're doing our prediction, you give me all the training data. You give me the new point, give me Alice. And then you give me the k value, like 3. That's what it's going to do, right? It's going to give back blue dot. That's our job. If we can do that, we've created the k nearest neighbors classifier. You can parameterize it so that you can change what k is. You'd be like, use 5, use 1. It'll be very easy to show you the difference, because all that is, right, is dealing with this table. Like, you sort it and you just take the top k things. We know how to do that, right? Take the top k things, look at the class column. That's what the code's going to look like. So I highly encourage you to try to look behind, because technically that was all in this code up here. I'm going to do things slightly different with slightly different names maybe, but more or less, this is what it was doing. But we're going to make this function. That is our goal. And then we can test it, because we can try every point in our test data set, do k nearest neighbors on it, and see how it compared, because we had those things labeled. We had their test set still labeled with the class. We just won't look at it for a second. All right? So that's where we're going, and I think I have rambled enough, and that's a good place to stop for the day. Does that make enough sense? Any questions about that? So that's the goal. We want to make this kind of function. Like, all right, you give me the training data, you give me a new point, like Alice, you give me what k is, and I will predict for you the class of that point. That's my classifier, the k nearest neighbors classifier, where you give me a value for k. All right? And yeah, you can evaluate your k nearest neighbors classifier on some test data that you want to set aside. You want to use your entire data set as your training data. That's why we save some around, so we can compare k nearest neighbors to some other methods that maybe exist in the machine learning universe that you won't be learning about in this class, but maybe you one day will. So yeah, this is a good one to start with, and that's a good place, I believe, to stop. So let me mark that we stopped there. To be continued. But that, I like to color this in for some reason. And so we will be ready when we come back next time for that. We'll pick right back up where we left off. And let's see, where were we? Essentially, I'll just draw a line to mark where the lecture ended. But that's a decent stopping point, I think. So if we are happy, I think I will stop the recording. And we will continue with this next time.